So as I mentioned today, we are pleased to present Louise and Craig Kirstens, who are going to talk to us about managed Postgres through CrunchyBridge. There are a number of managed Postgres options. CrunchyBridge is the newest, I believe. And we thought this would be a good opportunity for an overview of managed Postgres in general. Craig, you have the stage.
Perfect, thank you. So I'll give a little bit of background on myself. Today, I don't want to give kind of a deep dive product pitch, but I figure it's useful to give a little bit of product context and then gonna hand it off to Louise to go into all the interesting stuff about how we built it, how we designed it, how we architected it. A little bit of background on myself. I run product at Crunchy Data. Previously ran product for all of Azure Postgres, ran product at Citus Data, and going way back about 10, 11, 12 years or so now, was part of the original Heroku Postgres team and helped build and scale Heroku Postgres before Amazon even had RDS. So for better or worse, I've just been running Postgres for people in the cloud for north of 10 years, which, you know, when the cloud works, it's nice. And when it doesn't work, it can make for some really long days. I also curate Postgres Weekly. That's targeted kind of more towards an app dev audience than a DBA audience, but kind of like quick rundown weekly email newsletter of, you know, here's interesting articles and posts about Postgres. So a little bit of background context on Crunchy, and then we'll dive in a little bit on CrunchyBridge. Crunchy's actually been around for over 8 years now. We've been in our early days very focused on the government space, and now have a number of large enterprise customers. Essentially, our goal is to kind of be, you know, the Postgres people. We've got over 10 contributors to Postgres on the team. We employ folks like Tom Lane and Peter Gagan that work full-time on just open source Postgres. We've got others like Stephen Frost and Joe Conway doing a mix of open source as well as product development. So a pretty great team that's built a lot of things. And our goal is really, you know, if there's a Postgres problem, we can probably help you solve it. In terms of products, we've really got a few main offerings helping support you on, you know, bare metal VMs, on Kubernetes via our Kubernetes operator. And then more recently, myself and team came on to build out CrunchyBridge, a fully managed database as a service. And so if you're, you know, the really high level, what is CrunchyBridge? You'll hear us talk about it kind of throughout, and Louise will talk way more in the under the covers details, but it's kind of just yet another fully managed Postgres service in the cloud supported by Crunchy. And so, I mean, the first question I think is why would we build a managed service? Like, what's wrong with Heroku Postgres or RDS? And what if you want to self-manage? Crunchy's been focused on Kubernetes for a while. And a question I got a lot personally is like, haven't you done this before? Like, you've literally done this 2, 3, this is maybe your 3rd or 4th time building a database as a service. And, you know, part of it is I told people when I kind of came on board at Crunchy, I felt like there was a little bit of unfinished business from what we started at Heroku. Heroku was the first database as a service to exist for a SQL database. It predated Amazon RDS. At the time, we had all these Ruby on Rails developers asking for a database service, and we thought, you know, how hard could this be? It turns out it was a lot more work than we expected. But there was a lot of kind of interesting thoughts of, you know, how could you know, run git bisect on your database to tell when query results changed? And how can we make it, you know, trivial to scale up and scale down with no downtime, right? Hold your connections at a PG bouncer level so that queries just wait, nothing's dropped on the application side. So a lot of interesting kind of lofty goals, and we accomplished some of those, but I think there was a little bit more that we could have done there. And looking at the space, I look at something like an Amazon RDS. It's not bad, there's nothing wrong with it, but it's definitely limiting in a few ways. So really quickly, kind of reason number 1 why we went and built another database fully managed service. This is really for the big enterprises out there. I talk to them a lot, and it's funny because they'll have a conversation with, you know, Acme Corporation, and they'll be all in, and they signed this major commitment with AWS, and their executives, had this big partnership, and now they're going to standardize and move everything from on-premises to AWS. And I'll come back for a conversation with them in 4 months, and I'll start talking about AWS, and they'll cut me off and say, Craig, why are you talking about AWS? We're standardizing on GCP. And I'm like, wait, hang on, didn't we have this conversation 4 months ago? They're like, yeah, we have a new VP of engineering, and they have a buddy over at Google who runs this department over there. So now we're all in on Google. And this happens way more in large enterprises than you'd expect. Normally, if I was in the room, I'd see a few heads nod and a few groans of, yep, I'd been there, and that was really painful, because databases don't move as simply as you think. And the feature set of RDS is not the same as the feature set of Azure. If you want in-place upgrades, you've kind of got one option across all three of those. Whereas CrunchyBridge, it's supported right out of the box. And a big part of our goal is feature parity across all the clouds. So if you need to move, it's simply spinning up the read replica and coordinating your failover to the other cloud. A common question I do get is, do you support HA across clouds? Not out of the box. You very much could run it for a disaster recovery scenario. It's one of those things where going across cloud, the latency and just kind of transaction requirements get a little trickier, but it's possible someday. We just don't support it out of the box today. One of the other big reasons is pretty much all the major cloud vendors give you this sort of super user role that can do a lot of things, but if you really, really go deep with Postgres, there's something that you run up against and you can't do. Some of the major cloud providers don't allow you to have like a logical replication slot, so you can't use things like wal-e to JSON or PG output with Debezium. We're big fans of Postgres. I'm a huge fan of extensions. Will, one of the engineers on my team, every 6 months or a year, he's like, yeah, you're always a fan of extensions. It's not like this is new. You've been on this thing for, this kick for 5 or 6 years. And I absolutely have been. I think extensions are fascinating. You can add things like time series data. You can add, rich geospatial support. You can do things like sharding with Citus. There's ones that are fun to say, like hyperlog log. And so there's a really rich ecosystem of extensions where I expect our support to kind of be well ahead of the other major cloud providers. And if there's an extension you want supported today that we don't support, ask the question and we can probably have it for you in a week or two. The usual question I get is like, well, what if I want to write my own extension? Which I didn't expect to get that question a year ago when we started building the service. Turns out people are building way more extensions for their own purposes and specialized kind of use cases than I ever expected. And we're definitely thinking about, a world where you can bring your own extension and run it on top of us. PL Python, I like SQL. I write a lot of SQL. I don't mind SQL. I don't love writing PL pgSQL. PLR and PL Python are interesting to me, and I think PL Python in particular is very much so. With data science kind of being what it is, a lot of people will go and take, install Debezium and do change data capture from Postgres into Kafka, feed that into Spark, and run models on their data. That's great. You can do interesting stuff in Python that way, and then you run your model and you feed it back into, Redis or Postgres. But now I'm running like 4 systems just to run some basic model. And about 2 weeks before we were launching CrunchyBridge, I started live tweeting of like, I just kind of wonder what I can do inside Postgres with PL Python. And this could have gone horribly for me. Like I didn't know that this would actually work, and I was live tweeting it. I couldn't find the exact one. I found one from a few days later, but started live tweeting various bits of Python code, putting that into PL Python. And in about 2 hours, I had a probably terribly non-performant, but it was at least 20 lines of code, a recommendation engine inside my Postgres database. If I've got a small database, like on some hand, this is absolutely crazy. You shouldn't push this to production, but I'm pretty sure you could actually do a few optimizations and this would be perfectly fine to run on the fly or run as a batch job with pgcron or that sort of thing. And I'm a database guy. I like databases, and I think we should be able to do more with them. We don't have to shy away from it. I think, Louise will talk about this more of like, we should leverage the database for what it can do and not pretend like we have to do everything up in this ORM abstracted layer. Like SQL is a good language, and when you can do more things closer to the data, that's really great. So that's kind of reason number two. Reason number three, we have a lot of people that contribute to Postgres. I see a lot of discussion of, how do we support open source? And open source is wonderful, but it can't make a business. Well, if you're running a database in the cloud, consider us for it. We have a team that can go really deep. I look forward to the day that I can, bug Tom Lane because like there's a bug that we discovered from a user running on CrunchyBridge. We haven't run into any of those bugs yet, but from my days at Heroku, when we ran over 1.5 million Postgres databases across all our customers, like you run at that scale and you see a lot of odd things. So a 100 million problem was once a week. We've got a team that can dig in and really improve Postgres for the better that way. It's not we're going to take and fork Postgres. We're going to go and dig into the issue, and we're going to show up on the mailing with a patch, and we've got a team that can contribute and commit that. So really quickly, what is CrunchyBridge? You have your choice of the cloud. Take your pick of AWS, Azure, GCP. It's fully production ready out of the box. Provisioning, simple. Backups are automatically taken care of for you. You have point-in-time recovery built in, so you can roll back to any exact moment in the last 10 days. There's monitoring and high availability. We have a SOC 2 compliance. We check pretty much all the boxes that you get on AWS, check many more than you get on GCP, on Azure. And our goal is very much open source Postgres. So it's not a sort of Postgres thing. It doesn't lock you in. It's truly open source Postgres. And then the kind of obligatory marketing slide that, marketing makes me show of, hey, how we have all the green checkboxes and all the things that we can do that others can't, but you can go fact check all of these, right? Take a look at, Python support or super user access, and the various things you can do. Our goal is to build a really feature-rich Postgres service. So if you want to learn more, you can go create an account on crunchybridge.com, read up on the product. If you have questions, you can easily find my email, find me on Twitter. But with that, a little bit of the product overview, want to go into, I think, what's much more fun, and I actually prefer to talk about than all the product features, that is how we actually designed and built the service. I think we've got a lot of experience in a team that was engineer number 1 and 2 at Heroku Postgres, in addition to myself, that we joke, building the same thing the third time around, we can do it a lot better. And there's some really nice, I think, interesting design patterns all hidden in there. So with that, I'm going to pass it over to my colleague, Louise. I can stop sharing, to dive in much, much deeper on how it all actually works.
Hi, so thank you, Craig, for the introduction. I can't share yet my screen. Yes, I can now. Okay, perfect. Okay. So yes, I'm going to talk about the architecture and the design patterns that we are using, how we do everything, what are the different bricks in this program that we did in CrunchyBridge. And so I'm going to dive pretty deep, but unfortunately I don't have 5 hours to go into the code and show you everything. So I'll go as far as I can. So about me, I'm Louise Grandjean. I am very impressed in Stacy's pronunciation. A lot of people, even French people, completely butcher my name. So I was very excited about that. I'm a Python, Ruby, SQL developer. I started Ruby, I guess, more recently, as I was mainly working with Python and Django. And for CrunchyBridge, most of our code is in Ruby. So I was pleasantly surprised at how easy it was coming from the Python world to get on Ruby. And so I work at Crunchy Data, and we're building a multi-platform Postgres as a service that Craig just introduced. So I love Postgres and I enjoy complex and modern SQL. And one of the reasons I was very excited about building CrunchyBridge was also because I want applications and developers to be able to use Postgres at its full potential. And I think that we are working on that. So about today. I will first introduce the technology that we use in CrunchyBridge and then go into the different bricks. You'll see that we use bird names. I don't have a good reason for that, but it was fun. And so we have owl, we have hawks, we have nests. Weirdly, to detect issues, we have doctors, which I think should be vets, but the renaming is in discussion internally. So yes, I'll explain what our bricks are and what is owl, the API, the architecture, and the components that are used to deploy, to spin up new clusters, to monitor, to deprovision, etc. And show you a very I have a state machine that I did to go into an example of provisioning a cluster to show you how it goes. And then the second part is on Hawk, which is the part that is used to monitor and detect issues on servers. And finally, I think both Craig and I will be answering questions. So we, as I was saying, we wrote most of the code in Ruby and Crystal. So with Ruby, we actually use SQL, which is a very, very good ORM. It allows you to, get objects which are interesting in Ruby, but also really supports every feature you can imagine in Postgres, which is exciting. A while ago at the last PGConf Europe, I did a presentation on different ORMs for Python and for Ruby. And SQL for the Python developers is pretty close to SQL Alchemy in the way it works. And we really wanted to have flexibility in what we do with Postgres. Because yes, big surprise, we have a Postgres database. We use Sorbet. I think it was originally a team at Stripe who started working on it. It's type checking in Ruby, and I really rediscovered how much I love type checking working with Sorbet. And Crystal, we use it for Hawk. It's fast, it's static type, so we don't even need an extra app like Sorbet. And it's pretty good with concurrency. It's very close to Ruby, so it was kind of easy to just start working with it. And so it's very light also, which is why we use it for Hawk. We deploy everything on Heroku, and so we have a Postgres database to store our data. So first, what is OWL? So it's written in Ruby, and it's the control plane in charge of provisioning, monitoring, and deprovisioning Postgres servers. So basically, we have an external API that you either can, as a customer, use, or it's when you go on the UI that is communicating with OWL, and OWL is in charge of sending the request to spin up your servers on AWS, GCP, or Azure. And so OWL is this brick in the middle that does most of the I don't know, intelligence of CrunchyBridge. We have an API that the platform, so the external API communicates with. So one of the choice that we made for the Ruby developers among you is we choose not to use Rails. We didn't need it. Rails is a Ruby web framework. It's the equivalent of Django for Python developers, let's say. And because we wanted something very light, because most of our work is not on the API side or on the website. It's really just the work on monitoring databases. And so we used instead Rhoda for request routing. And Rhoda is tree tool for sorry, I lost my words. Yeah, it's a routing tree, basically, and it's really fast and really light. And we also wrote a mini framework just to serialize and deserialize our data in proper structures, and Sorbet allows us to type check, so we are safe if we get wrong data or wrong types for creating a cluster. So that's it about our API. It's really not the main part of the code, as you can guess. I think we have maybe like 20 endpoints. I haven't counted them. It's provisioning, deprovisioning, adding replica slot, like read replicas, forking, point-to-time recovery, this type of endpoints. And so it's not that many of them. So I'm going to here show a little bit the architecture. So that's how the tables, I didn't show everything because we have many more, but I wanted to focus on the tables that are used to kind of bookkeep everything that customers create. And so first you have cluster, where you have a name, the storage, the instance size, the region, whether it's HA or not. And to each cluster is attached one or more timelines. And we have here Postgres servers that have also a timeline. A cluster can have replica slots for read replicas, for HA standbys. And so those replica slots also have a Postgres server running. Here we have a one-on-one relationship because we have servers that are not Postgres servers, that are Hawk servers. So we just make that, we do a simple join with most of the information on server, but then we have extra information here, like, you know, the timeline ID, or whether it's a push or a get server, this kind of things. And so in the server, we have the flavor, we have the network it's in, and it's linked to AWS instances, Azure VM, and GCP. I made this before we added GCP. Oops. So the network are the same. There are AWS VPC, Azure VNet, and GCP VPCs. You can add firewall rules, which is also an endpoint in the API, to your cluster. And so that's just what it looks like on our Postgres database, is those tables. And now we have internal components that are also in that database. And that's what I will be mostly talking about in the next 20 minutes, 30 minutes, I don't know. First, we have actors. Actors help us keep track of what actions have to be done on a server. So they have a target. It can be a cluster, a server, network, a timeline, and a strategy. And I'll talk about strategies in a minute. And strategies are things like cluster create, cluster destroy, await, server create, etc. And each and the label is the step it's at, and so the next step that has to be run by our process. So it can be entry point when it's at the beginning of a strategy. It can be installed Postgres packages, for example. Those actors have semaphores. Semaphores help us deal with concurrency, and I'll show you how and why in a minute. We have obstructions and deadlines that both help us debug. They are slightly different, and that's, again, I'll keep that for later. Factories. Factories, as are pretty common, and we use them to handle the creation of objects and actors. So the clusters, the factories are really just here to insert into our database the right elements, the right rows, and order actors to start running. They are not themselves handling API calls. A factory is not going to spin up an instance on GCP, for example. So what happens is when we receive an API call to create a cluster factory, for example, it's going to use the cluster factory with parameters like your region, the storage, the platform, the whether you want high availability or not, and insert the right elements, and then order to our processes to run the right strategies and spin up all the right VPCs and servers, etc. So I wanted to show you an example of the cluster factory and how step by step what it does. Okay, so zooming in at the beginning, so we have a cluster factory create that is doing a Postgres server factory create. And the Postgres server factory create is actually also has two factories that it's itself creating. So one is the timeline. So it's going to actually pretty simply insert a timeline and then start the timeline create strategy. Again, to start a strategy, what we do is insert into the actor table the ID of the target, which would be the timeline here, the strategy and the label, so the step it needs to enter in. So that would be here timeline create and entry point. In parallel, it needs to also do the same for servers, and so it's going to start the server factory. The server factory needs a network, so it's going to insert the network row and not the server row. It's a mistake from my side. I am sorry, but I think I made a slight mistake. Oh no, never mind. Okay, so we insert the network here, and then the network needs to do a decision in terms of firewall rules that are initially present in the network. If we are ordering for something for a cluster that is completely open, it's going to have firewall open and insert 00, just this firewall rule, and then start just have the network created. So it's going to insert, now that we have a network and we have a server, it's going to insert the server row with a foreign key to the network that was just created. And then we, have all of those in the row, and so in the database, and so we start the actor, so the strategy server create that is going to be the one deciding, if it's an AWS or an Azure or a GCP instance, and spin up those. I will actually go into what happened in server create because I think it's an interesting one. I don't go into each and every step because it would probably be kind of hard to follow and maybe not the most interesting, but I thought it was overall maybe good. So here now we have the Postgres server, we have the server, we have the network, and we have the timeline. And so we can insert the cluster row with the foreign keys to all of this. So the main Postgres server, the network, the timeline, etc. There's also something that I didn't write here is if it's HA, it's then going to create the right replica slot for it and spin up the secondaries. And so now we can insert into our actor table a new row for the cluster create strategy that's going to start. And so now that we've been talking a lot about actors and strategies, I'm going to talk about them more precisely because I want to explain the difference between them because I guess that might be confusing. So the actor table is really here to keep track of running strategies. Then we have a process that we call bin workers that is here to run the strategies at the specific time that is kept in the actor table. So again, we have the label, that is the step that it needs to be run. We have the strategy that needs to be run, the target, and a time at which it needs to be run. Strategies are here to implement a workflow for a specific task. Each step of the strategy execute code So for example, you can have in server create the step install Postgres packages, and I think it's pretty straightforward what it does. And so install Postgres packages would be the label on the actor, and server create would be the strategy on the actor, and then we have the code for that strategy that is just in CrunchyBridge. And so once each step is done and successfully done, we transition to the next step. And so to transition to the next step, we update the label of the actor and the time at which it needs to be run, the next step. And then again, the process workers will catch that and run the next step. So we have over 50 strategies. Some of them are cluster create, server create, cluster wait. Cluster wait is kind of our default of, well, once nothing is really happening, we just regularly check if any background works need to be done, or sometimes we actually want to wake it up using Semaphores. And so, you know, one of the background tasks could be to do a resize. We have server await, Hawk server await, etc. And then the ones that are specific to the cloud platforms like AWS instance create, Azure VM create, etc. So as an example, I'm going to again have a state machine of server create. That is the strategy that spins up a server and install the right dependencies on it. So this is a simplified version of it, believe it or not, and I will zoom into it. So when we get at the beginning of server create, we create a deadline. I'll go into deadlines, but they allow basically to follow if something is wrong, and if something is wrong, we get paged. So when we start creating a server, we want to know if it's not working, if there's errors in some steps, if it's taking too long, etc. So we have this server create here, deadline. Then depending on the platform, if it's AWS, we will start AWS instance create, and then Azure VM or GCP instance create. Those are the strategies that actually spin up the servers. And so in server create, what we are going to do is wait for the server to have a public DNS. And then we do here a loop of, well, we're waiting for it. When it's okay, we're going to update the DNS records so that you have your I don't know what the name would be, but abc.crunchybridge.com and 5432, etc., so that you can pSQL. So we have our DNS records. And then we actually here again need to wait actually for SSH to be ready so that we can install the SSH keys. Then that's the moment where it changes a little bit, because I was mentioning that some of those servers are not Postgres servers, and so if it's not, we go into Hawk install. That's not what I want to focus on. So I want to look into what we do for Postgres. And so when it's a Postgres server, what we're going to do is install the Postgres packages and configure pgBackRest. And then we need to take a decision here whether it's a primary or a secondary. If it's a secondary, we are going to restore from the backup and then wait until the restore is done, write the standby signal, and then we can go back to the common end of the strategy. If it's the primary, then we can want to configure daily backups. Once all of this is done, we configure PostgreSQL itself, write the configuration, the pgHBA, etc., and then we can start. Here I kind of overly simplified because one thing that I would have been kind of just too much on this graph is showing what happens when it's a fork. Because after starting Postgres, what we're going to do is actually wait until until pgBackRest is done replicating, and then promote the new, what will be, the new cluster. So promote that server into a primary in a different cluster that the customer has access to. So it's a bit different, and I'm just mentioning here because I think we have time, but I have no idea what time it is actually. Okay. So now Semaphores. I've talked a little bit about it. So we use them to handle concurrency. So we have those semaphores that have a value. So in our table, we have a table Semaphores with an actor ID that it's linked to a name and a value. So the semaphores have a value that is incremented and decremented. So for example, we have a cluster. The default when nothing is happening is cluster await, and it will check several things. It will check if the semaphore's position for destroy is positive, or here I'm showing the example for failover. To check the position of the semaphore, we run this query, select one from semaphore where actor ID equals something, name failover and value over bigger than 0. So the reason we use them. So here is how it would work without and with semaphores. So here we are waking up the actor. So we are increasing the semaphore for the actor of the cluster and ordering it to fail over. What would happen is cluster await detects the semaphore change and transition to cluster failover. It performs the failover, and when it's done, the value goes back to 0, the value before it all started. Without a semaphore, we would just simply transition to just create an actor here, a cluster failover for that actor, and that actor would perform a failover, and that seems like it would be the same. However, we have one problem, is that we can have several processes running in parallel, and so we could end up with several processes incrementing at the same time this semaphore. And when we're using semaphores, then it would just simply check if the cluster await is has a value over 0, and in the semaphore query, it will transition once to cluster failover, and then when the cluster is done, it's decrementing to its value at the beginning of the transaction. So we will have one single failover, even if we have 10 processes that just in parallel order failover. Without a semaphore, we would be inserting actors for cluster failovers. So potentially we could be failing over again and again and again, and don't really know if we are ending up with the right primary or not. So semaphores help us solve this kind of issues of concurrency. Now deadlines. So deadlines have a target, again, like a timeline, a cluster, a server, and we create them to track issues. For example, no backups for more than 24 hours, or a server is still not up 20 minutes after creation. Just there's errors that we detected in our health checks, and yeah, we need to fix that. Some of them are because even if a restart or a failover didn't actually solve the issue, so we page the engineer that is on call. When a page is resolved, the deadline is destroyed. It's really useful for us to just kind of know what to look at, or at what step it's stuck. For example, on a create, it's really easy to just see what's going on. And we also have obstructions that are also here to help us debug. They're kind of different because they're not code dependent. A deadline could be because of something something that we did that is not working as we want. Obstructions are here to detect things like quota errors. it's very common that, you know, we could be spinning up a lot of AWS or instances, and then we reach the quota, and then this is tracked in obstructions. So that helps us just know that it's not on our side and that we need to create a ticket on AWS or GCP or whatever. And now what is Hawk? Here you have this amazing graph that my colleague Will made. So you have owl. Owl is watching hawks that are watching elephants, so Postgres servers. So Hawk is the part of our program that is written in Crystal, and we install them when we spin up new Hawk servers. We install it on the Hawk servers. That kind of makes sense. Each Hawk is in charge of watching Postgres servers that are in the same region, and every second it's performing several health checks. So among these health checks, we look at whether the server is reachable for SSH. If Postgres is up, we have a few queries that we run to check the health of Postgres. We also retrieve the LSN. Having the current LSN, last wal receive and last wal replay, helps us figure out also if there's something wrong with replication, if we have a secondary that is lagging behind when it shouldn't be in theory. And so we get warnings about that, and also disk usage, because, you know, when Hawk gives us data that helps us decide whether we need to failover or not. But for example, if the disk is at 90% or 100%, we know that failover wouldn't actually help. So that helps us. Each of those tests of those health checks gives us a little bit more information to understand what's going wrong, what's wrong in the server, if anything is wrong. And then on Owl, we have a process, Nest, that is used to monitor the servers. So it maintains SSH tunnels to the Hawk servers and retrieves the errors and failing servers from Hawks, and takes decisions using the doctors to restart, failover, also give information on what we're working on right now is making sure that we also can give some information to the customer of, like, for example, for them to have warnings on disk usage, so it's not a surprise of like, oops, it reached 100%. So we're working on this kind of things with Nest and Hawk. And then it creates pages for failing servers. Actually, it creates deadline, sorry. And it will try to first resolve those deadlines through restarts or failover. And then if that didn't actually work, then we get paged. That's it. So I think that Craig and I are available for questions if there are any. I hope that everything made sense. Yes.
Yes, great. Thank you both so much. So I am looking over at the chat. Are there questions? I don't see any queued up, but let's see. Okay, well, you both did such an amazing job explaining everything. There are no questions. Goodness. Oh, no, wait, we do have a question. Yay. Does the system support major version upgrades? I assume that's major Postgres version upgrades.
It's coming very soon. One of the perks of launching a new service is we can start with the newest, latest, greatest versions of Postgres, so we don't have old versions of Postgres to upgrade. So most of our customers are all kind of 13, nice and fresh. Yeah, PG upgrade is coming. That'll be the mechanism for in-place upgrades, so you don't have to do anything kind of dump restore or more complicated.
Terrific. Okay. Let's see.
Service, did I hear the service is dependent on Heroku? Owl is deployed on Heroku. the reason where we went with Heroku and we could move if at any points we need to is that I think both Dan, Will, and well also so I guess the three of us like the way that you can really easily parallelize processes. So we have this nest and worker processes. The worker is the one that is going through actors, and nest is the one watching health. And so we can just, if we have a lot of servers that need to be watched, we can parallelize that very easily. So that's why Heroku was so convenient.
Yeah, the database itself doesn't really touch or use Heroku. Like your data never touches Heroku or lives there. It's more of just and I expect if you talk to us in a year from now, there's a good chance, many of those services are not on Heroku other than just like the web app front end. Still a fan of Heroku for running quick and easy apps, and it's good for kind of a more user-friendly Kubernetes, more or less. A lot of things you don't have to worry about, but so there are pieces today there, but I think dependent is a little complicated because the databases themselves are never actually on Heroku or touch Heroku at all.
Cool. That's great. Okay, let's see. Checking the chat. We have a thank you. Are there any other questions? It was a really great comprehensive overview. Really appreciate it. And we have another question. Did you consider building it on top of the Kubernetes operator?
Yeah,
so,
oops. First, you want me to? Yeah, so I mean, there was some consideration there. I think the difference is at the scale we're going to operate, certain things become more costly there, and a lot of this is how much we can kind of push down any of our costs under the covers, which means we can run a cheaper service for our customers, right, and give you a cheaper price. I would say like Crunchy kind of has a flexibility of offerings. Like if you're running, one Postgres server on, bare metal, we've got, Crunchy HA Postgres, which takes care of, HA and backups and monitoring and all that kind of turnkey for just a few servers. We have a number of large enterprises running kind of an internal database as a service, but still not quite the same thing. It's, they're running 100 databases, and Kubernetes works really well there. I'd say if you're running and managing, tens of thousands, hundreds of thousands of databases, I'm sure Google can pull it off. I don't know that I want to manage Kubernetes at that scale. So at that scale, kind of custom define things, and we're really specialized towards Postgres, not just generic infrastructure things. We're not running apps and other things. It's just Postgres, and by doing it really natively, we can offer it, just as high of a quality in a faster way with lower costs under the covers. Louise, did I miss anything there? Anything else you want to add on?
No, that's pretty much what I was going to say about the fact that we are potentially managing thousands of databases, and that adding a layer makes debugging potentially harder, and all the things you said.
Okay, great. Let's just check over on the chat. Any other questions? Sorry if I missed this earlier, but for migrations among clouds, do you use logical replication?
So I was expecting Louise to go on that one, but cool. So it's a standard Postgres streaming replica. So it's not the logical piece. It's just a standard kind of wall streaming of a read replica from one cloud to another.
Okay, great. Let's see. What kinds of affordances does Ruby have that help you do the concurrency well? I'm curious because lots of people are using tools like Rust or Go.
I am sorry, but I don't know. I think we went with Ruby. One of the reasons we didn't want to use Go for CrunchyBridge is that right now we are a team of 3 people working on OWL, and we wanted to still have a shell that we can easily just go to, like Python shell, but for Ruby, so the pry, and Go doesn't really have that. And it's for us to be able to manage, potentially many customers with a small team. We really didn't want to give up on the shell.
Great. Okay, let's see. Next question. Does it have connection pooling? If so, which?
Yes. pgBouncer.
Okay, great. Let's see, next question. Oh, I think we may have gotten all of them. Anybody else have a question? I don't see anything in chat. Okay, great. Well, thank you, Louise, and thank you, Craig. This is really interesting. Even as a non-technical person, I found it really pretty easy to follow and kind of understand how it all works. Oh wait, we have one more question. What's the network architecture? How do I connect from my own VPC?
So by default, every database cluster is in its own isolated VPC. And if you want, so by default, we open it up to the world for ease of connectivity. There's way too many developers out there that like connect from their local laptop and do not know what their IP is. It's sad, but it's true in the world. So by default, it's open, so you can just connect in, but you can remove that rule and that locks it down. Then you can add kind of IP blocks and ranges. For VPC, we do support VPC peering. Today, the method for that is open a ticket, because we have to do this kind of handshake back and forth of send the invite and acknowledge, and then set up some private routes. That'll be coming in the future, self-service. It's actually sad. Not enough of our customers ask and want VPC peering, so it saddens me a little bit. It's like, hey, this is a good thing. You should do it. It's not that hard. Just set it up and you're done. So today, it's via a support ticket that we configure that for you. In the future, when we get enough demand for it, it'll be self-service.
Great. Okay. And all right. I don't see any other questions in the chat, so I think we're good. Thank you both so much. That was really interesting. And like I said, even as a non-technical person, I was able to follow it. So that always gets high marks from me. And there are people in the chat saying, thank you, nice presentation, so yay. For next month, we are scheduled for, we are moving to Wednesdays as of June. We'll be on the second Wednesday. So our next meetup is June 9 at noon. We are looking for a speaker. We thought we had one, but there was some communication confusion. And so we would love if any of you are interested or have someone you'd like to suggest, please drop us a note via Meetup, and we're happy to check it out. We would also like to thank PGUS, the United States PostgreSQL Association. Our Meetup is affiliated with them, and they do provide support for us. And also, just full disclosure, I'm also the president of PGUS, but San Francisco PUG is separate from PGUS, but it's part of the affiliated PUG. If you run a PUG and you're interested in getting affiliated, contact PGUS. And again, love to have a speaker. We are shifting to the second Wednesday. Thank you again to Craig and to Louise. Thank you everybody for coming, and we'll see you again in June.
Thank you, everyone.
Great, thank
Bye.
you.
Thanks.
Bye.